So sorry I can't be there today, guys. I'm going to make a video here where I go over the formula sheet with you guys so you can get that filled in. So hopefully that'll be helpful for you. The first couple things I have on here are just some general Desmos tricks that you need to know. The first is how to solve any equation in Desmos. It doesn't matter what type of equation it is. It could be used for anything. And that is just to enter the left side of the equation into the first line and that should say right side. Let's fix that on your paper, the right side of the equation in the second line. And then what you're going to do is you're going to look for the intersection of those two graphs. So intersection goes in that blank right there. And then your answer for this is going to be the x coordinate of the point of intersection. And you might have more than one answer. So let's do this example right here to see how that would work. So I'm going to take the left side of this equation and I'm going to type it into Desmos here. So I'm going to say y equals 2x plus 3 over x minus 1 plus 5 over x plus 3. So I type that into the left side into the first line, and then I'm going to take the right side of the equation and type it into the second line. So that's going to be y equals x over 1 minus x. And we're looking for the intersection of these two graphs. It's going to put some gray dots there where that happens. So if I zoom in just a little bit where we can see it a little bit better, you can see these graphs cross right here. So one of my answers is going to be negative 5.421. So x equals negative 5.421. And then I'm going to have a second answer for this because as you can see, you have more than one intersection. You also see them cross right here. You may want to zoom in a little more on that point right there because you want to make sure you're not getting one of those intercepts. You want to get this gray point right here where they cross, and that is negative 0.246. So if we go back over here, that's negative 0.246 would be the two answers to that equation. So that one in particular is going to be hard to solve by hand, so it is good to know that trick. The other thing that you're going to see that you can use Desmos for a lot is if you see a question that says what expression is equivalent to, or if it says simplify, you can just type the equation into Desmos and then type in your answer choices. So to look at that here for this problem, if I get rid of what I just had there, if I type in y equals 5 over x minus 1 minus 3 over x plus 2, and I'm going to zoom out a little bit so we can see that graph better, then I can just type in my answer choices. Y equals x to the second minus 8 over x minus 1 x plus 2. You can see those two are not the same graph, so that is not the answer. We're going to try B, which has the same denominator, but we got 2x plus 13 there, and you can see that is the exact same graph. So if I had time, I'd probably want to go through and check those others, but I don't want this video to be 2 hours long, so I'm going to keep moving. B would be your answer there. All right, so we're just going to go unit by unit and look at the different things that we've talked about. One of the first things we did was domain and range. Domain is your possible x values. Range is the possible y values. We talked about what made a function. A function is a relation where each x coordinate has only one y coordinate. If you're looking at a list of points, this means the x values do not repeat. And then particularly what we can tell with the graph is if the graph can pass the vertical line test, then it is a function. So if we can take that vertical line and move it across the graph and it only hits once at every point, then we do have a function for that. So In this section, we talked about inverses. Inverses are functions that undo another function. To find an inverse from a graph, you will graph the original function and then graph the potential inverse function. This might be answer choices that you're typing in here possibly. And then you want to graph the line y equals x. So that line y equals x in this graph I have over here to the side, that's this one. It's just that line that splits the first and third quadrants in half. And if the two functions are symmetric about the line y equals x, then they are going to be inverses. So if it looks like you could fold that graph in half and the two sides would line up, if you folded it on this dotted line right here, then those are inverses. So for example, over here, these two look like they are in fact inverses. Sometimes we might need to find an inverse from the equation. So you can do this by hand, or you can check your work using Desmos. So from an equation, the first thing you're going to do is you're going to switch your x and y coordinates in the original function, and then you're going to solve for the new y coordinate. So let's do that with a simple example right here. I've got y equals 5x minus 3. So I would say x equals 5y minus 3. And so I would need to add 3 to both sides. So I would have x plus 3 equals 5y. And then I'm trying to get that y by itself, so I'm going to divide both sides by 5, which we can just write like this, x plus 3 over 5. Or you may see it written like this. You may divide each one of those things individually by 5, and you might see it like this, y equals 1/5 x plus 3/5. Those two are equivalent to each other. Either one of those could be the answer. You can use Desmos to check your answer on this, what I was just showing you with the graph. If I graph the original equation, y equals 5x minus 3, I graph my inverse I just found, y equals x plus 3 all over 5, and the line y equals x, then I can see here y equals x is my blue line, and it does look like I could fold that graph in half. So that lets me know that I've probably done that correctly. So it's been a long time since we did inverses, but make sure you think about that. In Unit 1, we also learned how to solve absolute value functions. To solve absolute value equations, we have equations and inequalities. So equations is going to be first. The first thing you always need to do is get the absolute value bars by themselves. Then you will write two equations for the situation, and then you'll solve each equation for x. So here is an example. I've got 3 absolute value of x minus 1 equals 30. So before I can write two equations for the situation, I have to get rid of this 3 that's on the outside of the absolute value bars right there. So to do that, it's right next to the bars, which means it's multiplied. So I need to divide by 3 to get rid of that 3 right there. So I'll have absolute value of x minus 1 equals 30. Okay, now the absolute value bars are by themselves, so I need to rewrite this into two equations. The first one is just going to be x minus 1 equals 30. The other one is going to be x minus 1 equals negative 30. Okay, so we will add 1 to both sides of this equation, and x will equal 31. That will be one of our answers. And we will add 1 to the other side of this, to this other equation, and we'll get x equals negative 29. So the two answers that you have here are x equals negative 29 and x equals 31. Okay. When you have an inequality, something with a less than or equal to sign, or greater than or equal to sign, the process is similar but a little bit different. One thing you must remember is when you're solving inequalities, if you multiply or divide by a negative, you must flip the inequality sign. Okay, so the first step is still to get the absolute value bars by themselves. For these, you're either going to have an and problem or an or problem where you're looking for either where they overlap or you're just counting the two pieces together. So if you have a less than or a less than or equal to, that is an and problem, and you're looking for where the lines overlap. If you have a greater than or equal to problem, that is a or problem, and it's just going to be both. Okay. So once you get this together and decide which one you have, you're going to write two inequalities for the situation, solve each inequality for x, and then combine your answers for your and problem. So here's an example that kind of includes all of these things. The first thing you have to do is get the absolute value bars by themselves. So we would need to subtract 5 here. So we would have -2 absolute value of x plus 1 is greater than -12. We would need to divide by this -2 right here. And I'm dividing by -2, so whenever I do that, I need to flip that inequality sign. It was a greater than, I'm going to make it a less than right here, and I'll get a +6. All right, so at this point, my absolute value bars are by themselves. So I'm going to write this as two equations. So I will have x plus 1 is less than 6. This is a less than sign, so it's and. X plus 1 is, here I have to switch this to a greater than, -6. So you want to flip that inequality sign and make this negative. And so I'm going to solve this by subtracting 1 from both sides, and I'll get x is less than 5. And over here, I'm going to subtract 1 from both sides, and I'll get x is greater than -7. So if you think about what we've got here, we got our -7 and our +5. So I've got x is less than 5, but it's also greater than -7. So we're looking at the numbers in between -7 and 5. To write the answer for that, we're going to put our lowest number first, use a less than sign, x less than sign 5. This would be our answer for that problem. Okay. Piecewise functions is something that we went over. It's really helpful to be able to type these into Desmos, but they're a little bit tricky. Whenever you type these into Desmos, you are going to do f of x equals, you're going to use squiggly brackets. You're going to put the first domain, we'll call that domain 1, and then you're going to put equation 1. And so, for example, in this one right here, this is domain 1, and this part right here would be equation 1. And then you will do a comma, and then you'll do domain 2, and you'll do equation 2. And so this part right here would be domain 2 and equation 2. So let me just show you what that looks like whenever we type it in. I put what it should look like here, but this way we'll also be able to see the graph. So f of x is going to equal squiggly bracket. So domain 1 is x less than 0. We're going to do a colon, and then we got to do -2x minus 3, our equation 1, and then we're going to do a comma. And then we'll do our second domain, which is x is greater than or equal to 0, x is greater than or equal to 0, colon, and then our equation 2, which is going to be, let's see, 1/2 x plus 4. And what it'll do for us here is it will graph the piecewise function. Just remember, it does not give you the open or closed circles on the end, but it'll give you a general picture of what this looks like. And it also makes it where, like, if I need to evaluate this, if I need to find f of 3, I can just type in f of 3, and it'll give it to me. Or if I need to find f of -2, it will give me the answer there as well. So it can be very helpful to be able to type those in. We also did function operations. So if I have something that says f plus g and then parentheses x, that means we're just doing f of x plus g of x. And in a similar manner, here this is going to be f of x minus g of x. F times g of x just means f of x times g of x. And then f over g of x means f of x divided by, that'll be a fraction, g of x. I didn't leave enough room to write fraction on here well. You may see a problem like this where you're asked to find 2f plus g of 3. First of all, you may want to think of it this way. 2 times f of 3 plus g of 3. So both of those you're finding, you're plugging in 3 into both of these. So this is not that bad to do by hand. You would just do f of 3, which would be 3 times 3 squared minus 5. 3 squared is 9. 9 times 3 is 27. I'm going to subtract that 5, so we'll get 22 there. And we would want to find g of 3, which is going to be 2 times 3 minus 1, which will give us 6 minus 1, which will give us 5. So what we would do here is we'd have 2 times f of 3, which was 22, plus g of 3, which is 5. So we got 2 times 27, and 2 times 27, I believe, is going to be 54 for our answer there. You can also do this on Desmos, so let me show you that real quick. If you type in your equations, f of x equals 3x to the second minus 5, and g of x equals 2x minus 1. You have to call them f of x and g of x. It won't do it correctly, I don't believe, if we type it in like that. But if we type it in the way I have it on that second line, like this, it will give you the answer straight off. So that's always an option for this as well. All right. And the last thing from Unit 1 was function transformations. If we have something where we add 7 to the end of the graph, that's going to move the graph up 7 units. And of course, this number could change here. It could be 10, it'd move up 10. If it was negative 4, it'd move down 4. If we have f of x minus 4, whenever we put a number on the inside of the parentheses right here, it's going to move the graph left or right, and it's going to go in the opposite direction. So since we have a negative 4, usually negative would make us think left, but it's on the inside of the parentheses, so we want to go the opposite direction. This will go to the right 4. If we put a negative out in front of our equation, it is going to reflect the graph over the x-axis. It's going to flip it upside down. If we have a number out front that's multiplied, that's either going to stretch out or shrink down our graph. This will expand the graph vertically by a factor of 3. Or if it's a small number, if it's a number between 0 and 1, it's going to compress the graph vertically by a factor of 0.1 for that. So that covers everything sort of from Unit 1. We'll move on to Unit 2. In Unit 2, we looked at logs and exponentials. The log is written this way, and it goes with the exponential where the base is the base of your exponent, the a goes here, and the x goes on the other side. Common logs are a type of log that we looked at, and common logs are written like this. They're just like log x. They don't have a base on them. So when you see that happening, the understood base is 10. So even though it's not written there, it is understood that there is a base of 10 right there on that log. Natural logs are written this way, natural log of x, and they also don't have a base written, but the understood base is e. So even though it's not written there, we know that there is a base of e right there. Let's do that different color. Right there. Okay. So if we're asked to solve a log equation, I'll go back over this real quick. First of all, you could type this into Desmos. So I'll show you how to do that here in a second. You can solve any equation with Desmos. But if you're doing this by hand, you're going to do, to get rid of a log with a base of 3, you're going to do 3 raised to that power on both sides. And that will give you x plus 2 equals 3 to the 2.5. So if we type that into Desmos, 3 to the 2.5, we're going to get this big number, 15.588. And then we are going to subtract that 2. So x will equal 13, well, 13. Why is it not working? 13.588. Remember, you can do this in Desmos as well. So if I pull this up over here, get rid of everything I have here. We'll type in y equals the left side, log base 3 of x plus 2. And I got to do y equals 2.5. Don't leave off the y equals or it won't graph it. And then I'm looking for where these cross. That happens right here, 13.588, which is what I got as my answer. So if you need to rely on Desmos, do. It'll work for this. Okay. We talked about domain and range of this. For the domain of an exponential function, you always have a domain of negative infinity to infinity, or it might be called all real numbers. And in a similar manner, the range of a log function is always negative infinity to infinity, or all real numbers. Okay. Exponential functions are always going to have horizontal asymptotes, and log functions are always going to have vertical asymptotes. So those are some things to remember that can help you answer some questions there. We did do compound interest. I just wanted to put that formula here for you guys to remember. Compound interest in this formula, A stands for your amount or your balance in your account. P is your principal, which is your starting amount that you start with. R is your rate as a decimal. So for example, if you have 6%, you would change that to 0.06 before you plug it in. N is the number of times compounded per year. So if you are compounded monthly, that N would be 12. Or if you compounded weekly, N would be 52. T is going to be your time in years. And so that can be used for your compound interest formula. Okay, moving on to Unit 3. In Unit 3, we talked about factoring and dividing polynomials. So we did that long division that was really difficult to do, but there's a way around having to do long division for a lot of problems. The remainder theorem is very useful. It tells us if a function f is divided by x plus 3, I used a specific example here, then the remainder will be f of negative 3. So notice this was a positive 3 here, and I plugged in a -3 into the equation. So here's an example right here. If I have, what is the remainder when x to the third minus 4x plus 2 is divided by x plus 1? I could use long division to figure this out, but that long division is kind of difficult and takes a while. So if I use remainder theorem, I just need to look at this factor and take the opposite sign. So I need a -1. So I'm going to do -1 to the third minus 4 times -1 plus 2. -1 to the third is still -1. -4 times -1 is +4, and I've got a +2. So that's going to be -1 plus 4 is 3. 3 plus 2 is 5. So my remainder here is going to equal 5 whenever I divide those two. Okay. In conjunction with remainder theorem, when a function is divided by a factor of that function, the remainder will be 0. So to use remainder theorem for this, if I have a question that says, is x minus 5 a factor of 2x to the third minus 9x squared minus 5x, then what I can do is I can look at this number right here, and I can take the opposite sign, and I can plug it in. So I have 2 times 5 to the third minus 9 times 5 squared minus 5 times 5. And the numbers are going to get a little bit big on that, so let's just type that into Desmos. 2 times 5 to the third, on the outside, third minus 9 times 5 to the second minus 5 times 5. And you see we get 0. And so since this equals 0, that means that the remainder is 0. And if the remainder is 0, then x minus 5 is a factor. It divides evenly. So we would say yes for this. X minus 5 is a factor. Okay. We also looked a lot at the graphs of polynomials. When we talked about polynomials, we talked about the degree of polynomial. So the degree of a polynomial is the value of its highest exponent. So if you have something like x to the fourth, and that's the highest exponent, then that would be fourth degree. The x-intercepts of a function can be called several different things. Sometimes they are called x-intercepts, but sometimes they're called zeros. Sometimes they are called roots. And sometimes they may be called solutions. Although usually it's given to you in an equation form if they call them solutions and not like a function form. But these are all going to give you the places where your graph is going to cross the x-axis. So a function with a degree of n will have n roots. So if you have a fourth degree function, then it has 4 roots. They might not be all different roots. You can have roots that show up more than once. They can have a different multiplicity, but you will have that many roots. Remember that imaginary roots always come in pairs. And as I said, that you can have a different multiplicity, so they could be there just one time, or they could be there 2 times, or 3 times, or 4 times. That's called the multiplicity. A root with even, oh wait, no, sorry, that's backwards. A root with odd multiplicity, so 1, 3, 5, 7, is going to cross the x-axis whenever you graph it. But a root with even multiplicity will just bounce off of the x-axis, so it'll do like this. If you have odd multiplicity, it'll cross. If you have even, it will just sort of go down there and touch, but not actually cross. So this first one right here, this would be what it would look like if you had odd multiplicity. This is what it looks like if you have even multiplicity. Okay. And then I'm going to do unit 4, and then I am going to quit before this video gets way too long, and we'll look at the rest of this tomorrow. So for unit 4, you have rational functions. For rational functions, it's really a lot about fractions. So to add or subtract fractions, remember that you must have common denominators. For that, so you have to get those denominators the same before you can add and subtract. For multiplying fractions, though, you do not have to have common denominators. Okay. To multiply, you're going to multiply the numerators together and multiply the denominators together. So you can just multiply straight across whenever you're multiplying. You do not have to have common denominators. And then for dividing fractions, it's easy as pie. You're just going to flip the second and multiply. So you're going to use those same rules for multiplication. So you're welcome to go through your notes and fill in the rest of this, but I'm not going to make a video for it right now because the video is going to get really long. But we have several other things that we need to look at that we will look at on Thursday. If you have any questions, feel free to email me. I'll try to check my email throughout the day.